Have you ever experienced a sudden network outage, perhaps at work or when accessing an important online service? It is incredibly disruptive, isn't it? Such interruptions can halt critical operations, cause significant financial losses, and severely damage reputation, highlighting how truly vital uninterrupted network access is in our interconnected world. Hardware redundancy in networks works by duplicating critical components to eliminate single points of failure, ensuring that if one part fails, another immediately takes over without interrupting service. The core purpose is to maintain continuous network availability and provide fault tolerance, which means the network can continue operating even when one or more of its components encounter a problem. The fundamental principle behind hardware redundancy is to prevent a single hardware malfunction from bringing down an entire system or service. When we talk about networks, this involves duplicating devices like routers, switches, firewalls, and even power supplies or network interface cards. This duplication can take many forms, from an active standby setup where one device is operational and another is waiting, to an active configuration where multiple devices share the load. The system constantly monitors the health of its active components, and upon detecting a failure, it automatically triggers a failover process. This transfer of function to the redundant component is typically very quick, often transparent to the end user, and aims to minimize the mean time to recovery, thereby vastly improving the overall network reliability. Implementing hardware redundancy involves several practical steps in network design and deployment. For example, you might use two routers configured in a high-availability cluster, such as with the Virtual Router Redundancy Protocol, or VRRP, where one is active and the other is standing by. If the active router fails, the standby router instantly assumes its role using the same IP address, preserving network connectivity. Similarly, servers can have redundant power supplies, which draw power from separate power distribution units, or PDUs, ensuring power continuity. Network interface card teaming, or bonding, allows multiple network cards to act as a single logical interface, providing both increased bandwidth and fault tolerance if one card fails. Even storage systems like storage area networks, or SANs, employ redundant disk arrays through RAID configurations to protect data from disk failure. These sophisticated redundancy strategies are critical for achieving high availability, often expressed as a percentage of uptime like 99.999%. This level of reliability is paramount for mission-critical applications and services where even a few minutes of downtime can be catastrophic. Beyond simply duplicating devices, careful planning for diverse network paths and geographic redundancy, often referred to as disaster recovery, further strengthens network resilience. While introducing redundancy does increase the initial cost and operational complexity, the investment is justified by significantly reducing the risk of costly outages and ensuring uninterrupted service delivery. Ultimately, hardware redundancy is a foundational element of robust network design, transforming a potentially fragile system into a resilient and continuously operational infrastructure. By carefully duplicating components and implementing intelligent failover mechanisms, network architects create environments that can gracefully withstand unexpected failures. This proactive approach safeguards network performance and availability, which is essential for supporting the relentless demands of modern digital operations and the critical services they enable.
If you love understanding how the web works, like, subscribe, and stay connected with us.